Welcome to tonight's video on non-arithmetic and non-geometric infinite series. Recall that we've found the sums of partial sequences that are arithmetic and geometric, but we're also now going to do it if it's neither of those. And in order to do this, there's a 5-step process, and we'll go through it. So the first of that 5-step process is to list the first 5 terms of the sequence. So the first term here, if I put 1 in, 4 plus 1/2 is 9/2. And then if I put 2 in, I get 1/4 because 1/2 squared, so 4 plus 1/4 is 17/4. And then 1/2 to the third is 1/8, so 4 plus 1/8 is 33/8. And then if I put 4 in, 1/16 plus 4 is 65/16. And then last but not least, if I put 5 in, so 132, so 4 plus 132, or 4 plus 1/32 is 129/32, I believe, because 32 times 4 is 128, so plus 1 is 129. So those are the first 5 terms of the sequence. First 5 terms of the sum. So the first term of the sum is the same as the first term of the sequence, 9/2, and then you go 9/2 plus 17/4. So you get a common denominator, multiply by 2, so you get 35/4. And then you add 35/4 plus 33/8. So 70 plus 33 is 103/8. And then 103/8 plus 65/16. So 206 plus 65 is 271/16. And then 271/16 plus 129/32 gives you 671/32. Then the formula for the explicit definition, well, it looks like it's 2 to the n on the bottom, but the top, the first term is 9, but there's no real pattern because you add 26, then a whole bunch. So it's not possible here to find the explicit definition for the sum, but we do know the limit as n approaches infinity of the sum is infinite because it's going up forever and ever, so that does not exist because of unbounded behavior. And then the sum of the sequence is the same as the limit of the sum. Since it's 4 plus 1/2 to the n, and that's equal to infinity, which means it does not exist. Alright, so that's the process that we're going to use to find the sum of a non-arithmetic, non-geometric sequence. So number 2, the first 5 terms are 1/2, and then 1/6, then 1/12, then 1/20, then 1/30. And then the first 5 terms of the sum are 1/2. 1/2 plus 1/6, so 3/6 plus 1/6, 4/6, which is 2/3. 2/3 plus 1/12, so 3/4. 3/4 plus 1/20, so 4/5. And then you can guess the pattern, 4/5 plus 1/30 is 5/6. The explicit definition of the sum Well, if you notice, the numerator is n, the denominator is n plus 1. So the limit as n approaches infinity of the sum, which is n over n plus 1, observing highest powers, we get 1 over 1, which is just 1. And then the last thing is to find the sum, which is the limit of the sum, which is equal to the sum of the sequence, and that is equal to 1. All right, so number 3, find the sum when the sequence is equal to 1 over n. So the first 5 terms are 1, 1/2, 1/3, 1/4, 1/5, and then the sum is 1 plus 1/2 is 3 halves. 3 halves plus 1/3, that would be 2/6 plus 9/6, which would be 11/6. 11/6 plus 1/4 will then give us 22/12 plus 3/12, which is 25/12. 25/12 plus 1/5 is something over 60. So 125 plus 12 is 137 over 60. Once again, the explicit definition for the sum. Notice there's no real rhyme or reason here, so it's not possible. But we do know the limit as n approaches infinity of the sum. That's infinity, so that does not exist because of unbounded behavior. And then the sum is equal to the limit as n approaches infinity of the sum, which is the same as the sum of the sequence, which is infinity. All right, so number 4. So now, one of the things you'll notice if you look back up here is that to find a term in the sequence, like 1/3, you could take the term in the sum and subtract it from the previous term in the sum. So 11/6 minus 3 halves would give you 1/3. So basically the formula to find a sub n is equal to the term in the sum minus the previous term in the sum. So if I use that same logic here, it's the term in the sum minus the previous term, which means here you're going to take n over 3n minus 1, because that's s sub n, minus, and now you're going to put s sub n minus 1, so n minus 1 over 3 times n minus 1 minus 1. So now you got to get a common denominator after you simplify and get 3n minus 4. So you multiply this side by 3n minus 4. And subtract here and multiply by 3n minus 1. Then you're going to simplify, so you get 3n squared minus 4n. Here you're going to FOIL, so 3n squared minus 4n plus 1, but then you distribute the negative, so it's 3n squared plus 4n minus 1 over 3n minus 1 times 3n minus 4, which means when you cancel those out, you get negative 1 over 3n minus 1 times 3n minus 4. That is a sub n. So the limit as n approaches infinity of negative 1 over 3n minus 1 times 3n minus 4 equals, so if you want to simplify here, so you get negative 1 over 3n squared plus dot 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 dot. So if you observe highest powers, you get 0 over 3, which is 0. The limit of the sum, well, the limit as n approaches infinity. Oh, first of all, it asks if it converges, and the answer is yes, it converges. Because remember, converges means it has a limit. So limit as n approaches infinity of the sum, if you observe highest powers, that's equal to 1/3. And yes, it converges. And then find the sum of the sequence. I equals 1 to infinity of negative 1 over 3i minus 1 times 3i minus 4. So that's equal to 1/3. And yes, it converges. Because remember, the sum of the sequence is the same as the limit of the sum. And so the sum is just equal to 1/3. All right. So looking at number 5, this is actually arithmetic. So the first 5 terms. So we get 10, 13, 16, 19, 22, because you're just going to add 3 every time. So the limit as n approaches infinity of 3n plus 7, that's 3 times infinity plus 7, which is just infinity. First 5 terms of the sum, you get 10, 23, 39, 58, and then 80. Explicit formula for the sum, remember in an arithmetic sequence, it's n divided by 2. Number of terms divided by 2 times the first term plus the nth term. And remember, in this case, the nth term is equal to 3n plus 7. The first term I know is 10. So it's n over 2 times 3n plus 17. So it's equal to 3n squared plus 17n over 2. Then you find the limit as n approaches infinity of the sum. And you observe highest powers. That's 3 over 0, which is infinite. The sum of the sequence, and yes, this does, sorry, no, this does not converge because it's infinite. Same for part B as well, that doesn't converge. As far as part F goes, the sum of the sequence to infinity of 3i plus 7, that's equal to infinity, does not exist. Unbounded behavior, and no, it does not converge. And the sum would be infinity. So number 6, find a sub n again. So remember, that's equal to the term of the sum minus the previous term. So it's equal to negative 5n over 2n plus 1 minus negative 5 times n minus 1 over 2 times n minus 1 plus 1. So this would be 2n minus 2 plus 1, so 2n minus 1. So it's equal to negative 5n times 2n minus 1. This would be negative 5n plus 5. So it's going to be minus negative 5n plus 5 times 2n plus 1 all over 2n minus 1 times 2n plus 1. So when you simplify, you get negative 10n squared plus 5n. And then when you simplify here, you get negative 10n squared plus 10n minus 5n, so plus 5n plus 5, but then you have to distribute the negative sign, so it's plus 10n squared minus 5n minus 5. Then notice cancels out, so you get negative 5 over 2n minus 1, 2n plus 1. Then you gotta find the limit. So the limit as n approaches infinity of negative 5 over 2n minus 1 times 2n plus 1. That's going to be equal to the limit as n approaches infinity of negative 5 over 4n squared plus, and if you observe highest powers, that's equal to 0 over 4, which is 0. And yes, it converges. The limit of the sum when you observe highest powers is negative 5 halves, and yes, it converges as well. So the sum of the sequence, which is negative 5 over 2i minus 1 times 2i plus 1. Sum of the sequence is equal to negative 5 halves. So the sum is equal to negative 5 halves. Alright, that concludes our video for this evening. If you have any questions, feel free to ask in class. Have a good evening.